Hello. I keep forgetting that I'm streaming. I'm so used to streaming that I will just start streaming and then I'll look at something else and I'll completely forget what I'm doing. We have an Ivan in this lesson. Ivan. Ivan. Meow. Ivan is pretty funny because he's been an indoor cat for his whole life, apparently, I've been told. And so now he has the ability to go outside in my backyard and play around. And so he doesn't understand weather. And so I let him out this morning and he went out and then he came back in like 2 seconds later and he's all like, shaking his paws off. And he's like, meow. And it's like he's literally I feel like he's asking me to change the weather for him, please. He doesn't understand that I don't have control of the weather. It's kind of cute. Okay. So I'm going to go ahead and get started. So we're finishing up our reviews of the semester 1 content today. So the next topic I have to review is rotational dynamics. Okay. And the first concept from rotational dynamics is torque. Torque is denoted by tau, and it is equal to F perp times R. So what do I mean by that? Well, let's suppose you have some blob like this, and the blob has a pivot point. And right here, a force is being applied. So maybe that force is being applied in that direction. So there's the force. So what we do is we draw a line segment that extends from the pivot point to where the force is applied. The length of that line segment is R. Now, once we've drawn that line segment, we can take this force and we can break it up into a component that is perpendicular to that line segment and a component that is parallel to that line segment. And so this is F perp. Okay. If the torque would tend to rotate the object counterclockwise, then that is a positive torque. If it would tend to rotate it clockwise, then that is a negative torque. So this would be a positive torque. Gravity exerts a torque as well, and the gravitational torque acts as if it were coming from the center of mass. Okay. So let's suppose that the center of mass is right here. This is the symbol for center of mass. Then we would draw a line segment from the pivot point to the center of mass. The length of that line segment would be called RCM. Okay. The gravitational force acts downward with size mg. So there's a component of that is perpendicular to this line, which is this component right here. So that's the mg perpendicular. And so the gravitational torque is going to be mg perpendicular component times RCM. In this case, and it can have a positive or a negative sign. In this case, the torque is going to be negative because gravity is swinging it in the clockwise sense. So there's this idea of center of mass. So let's go ahead and remind ourselves what center of mass is. So xcm is basically the balance point of the object. And the definition changes slightly if you have a discrete system of masses versus a continuous system of masses. So discrete means that the masses can be numbered, like there's mass 1, there's mass 2, there's mass 3, etc. If it's continuous, then that means it has some linear mass density. It's, you can't identify one spot as being one mass and another spot as being another mass. So if it's a discrete distribution of masses, then the center of mass is defined as m sub I times x sub I, sum over all the masses, divided by the total amount of mass. Okay? If you have a continuum distribution, your center of mass is the integral of lambda of x times x dx over the integral of lambda of x dx. Okay? So this denominator right here, this is the same thing as m tot. And so just to remind you that lambda of x is dm dx. All right? Sometimes an object will be stated as having a uniform linear mass density. And if it has a uniform linear mass density, then this would equal a constant, and it would just be the total amount of mass times the total amount of length. Okay? Then we talked about rotational inertia. Inertia is measuring, so torque is like the twisting force, and inertia is like the natural resistance to being twisted, okay? So if something is spinning, it takes effort to make it spin faster, and it takes effort to make it spin slower. So that inertia is the measuring that. Okay, and so if you have a discrete system of masses, the inertia is sum over m r squared, where r is the distance from the axes, the perpendicular distance from the axis of rotation. And if you had a continuum distribution of mass, then this would be equal to the integral of lambda of x times x squared dx. So we learned a theorem involving the inertia that's called the parallel axis theorem. And this theorem appears a couple of times on the final, so make sure you know this theorem. And so let's suppose you have a blob, and here's the center of mass of the blob. Okay, and so you have some axis of rotation that goes through the center of mass. Okay, you have a parallel axis of rotation over here that is not going through the center of mass. The distance between those two axes is d. So it's the parallel axis theorem. So these two axes have to be parallel to each other. So I couldn't relate, for example, this axis to that axis because that axis is at a right angle to that one. See what I'm saying? And so what the parallel axis theorem says is that the inertia about the axis that doesn't go through the center of mass is equal to the inertia that goes through the center of mass plus md squared, where m is the total amount of mass of the block. So that's going to pop up several times. Then we talked about Newton's second law. For rotations. Newton's second law for rotations says that the net torque is equal to I times alpha, where alpha is the angular acceleration. So let me remind you the definitions of some of these angular quantities. There's theta, which is angular position. There is omega, which is d theta dt. That's the angular velocity. There is alpha, which is d omega dt. That's the angular acceleration. So if alpha is equal to a constant, then we have the equations of angular kinematics, which are identical to the equations of linear kinematics, just with some variables switched around. So in particular, we have delta theta equals omega initial times time plus 1/2 alpha t squared. We have omega final equals omega initial plus alpha t. And we have omega final squared equals omega initial squared plus 2 alpha delta theta. So those are only if alpha is a constant. So oftentimes what you'll find is that the net torque is 0, and so that means there's no angular acceleration. And we solved some problems that are called static equilibrium problems. Okay. And so for static equilibrium, the net torque is equal to 0, which says that it is not rotating. And then also, the net force is equal to 0, which means that it is not translating. Okay? And so this will result in a system of equations that will allow you to solve for the forces. Okay? So that's a common type of problem. Sometimes the object is not in static equilibrium, and so you have rolling happening. And so if the object is rolling, then you have a system of equations where the right-hand side is not equal to 0. So you have net torque is I alpha, and you have net force is ma. All right? And then these two equations are related by the fact that if you are rolling without slipping, then you have a equals alpha times r. So the linear acceleration is related to the angular acceleration. Similarly, we also have speed equals omega times r. All right. We talked about rotational energy. Okay. So your total amount of kinetic energy is equal to your translational kinetic energy plus your rotational kinetic energy. Okay. Now, these two things, you might have one or both of these two things. So if you think about a block is usually square. So it's not going to be rolling. So blocks tend to have only um, translational kinetic energy. If you have things like pulleys, pulleys tend to be fixed in place and spinning. So pulleys tend to have only rotational kinetic energy. You can have things that have both. Like, what about the Earth? The Earth is translating through outer space, and it's spinning while it translates. So it would have both. Something that is translating while rotating, if it's rolling, so the Earth is not rolling, all right, because it's not in contact with the surface. But if you think about a bicycle wheel is rolling. And so if rolling, this equation simplifies to 1/2 mv squared times the quantity 1 plus I over mr squared. All right. So these are used in energy problems. If you have an extended object and you need to compute, like a wheel, and you need to compute its gravitational potential energy, then that is going to be mg, and the y value we use is the y value of the center of mass. And we learned a nice equation for the y value of the center of mass. If you have like a blob, okay, and the blob is pinned right here, and here's the center of mass of the blob, and this is L. L is the distance from the pivot point to the center of mass. This angle is theta. So if we think about how much is the center of mass lifted up, we derived a nice equation that says that the height of the center of mass is equal to L times the quantity 1 minus cosine of theta. So you can use that to get the elevation of the center of mass of a extended object. Then we talked about angular momentum a little bit, just briefly. So angular momentum, there are kind of two types of angular momentum. So there's an orbital angular momentum, which is mv perp r. So I like to call that the orbital angular momentum. So that's like the angular momentum of a tether ball. So it's a blob that is going around a pole, okay? So the Earth has orbital angular momentum. That's the angular momentum associated with its velocity around the sun, okay? Then you have spin angular momentum, which is I omega, okay? So the Earth also has spin angular momentum because it's spinning about its axis. So the total amount of angular momentum of the Earth is the angular momentum of its revolution around the sun plus the angular momentum of its spin about its axis. Okay. Now, the nice thing about angular momentum is that it's conserved. The total initial angular momentum is equal to the total final angular momentum if there is no torque on the system. Torque changes angular momentum. All right. So then we had a lesson about power. Okay. Just a brief lesson about power. And so power is defined as the rate of change or the rate of work being done. I derived an equation for power based on that, using the definition of work. And that equation is that power equals force dot product with velocity. Okay. You can also have power if something is rotating. So for example, rotational power is torque times angular velocity. So that would be the power if you have an engine that is causing a drive shaft to spin, you could calculate the rotational power using that formula. Okay, so then we talked about simple harmonic motion. The equation of simple harmonic motion is negative omega squared times x minus c equals ma. So a is the acceleration, m is the mass. Oh, there should be no m here, my bad. The m has already been divided over to the other side. So minus omega squared times the quantity x minus c equals a. X is position. Omega squared is a constant that depends on the properties of the system. And c ends up being the equilibrium position. And so what I showed, okay, is that if the equation of motion takes that form, then your position as a function of time is equal to the following. It's equal to the constant plus a cosine of omega t plus phi. So omega and c are determined from the equation of motion here. Okay? Capital A is called the amplitude, and phi is called the phase. And so the amplitude and the phase are not determined by the equation of motion, but they're determined by the initial conditions. Okay? Because if you have something undergoing simple harmonic motion, it's not going to start moving unless you nudge it. Okay? Unless the experimenter nudges it, or unless the environment nudges it, something disturbs the system from equilibrium. And when that disturbance happens and how big that disturbance is are what determines the amplitude and phase, but not the system itself. It's something external to the system. Omega is related to the period according to the equation 2 pi over omega. So that's really useful to know the period of simple harmonic motion. Okay, so we looked at a couple of typical systems in simple harmonic motion. So we looked at the mass spring system, which is a spring of stiffness K connected to a mass M. Okay, and for the mass spring system, the period is 2 pi square root of m over k. So we derived that from setting up the equation of motion and showing that it had this form and identifying what omega was and then using this formula. Another system that we studied was a physical pendulum. Okay, which is pinned at some point. It has a center of mass here, and then there's a certain angle with respect to the center of mass. So that's called a physical pendulum. This length is RCM. And so the period of a physical pendulum is 2 pi square root of I over mg RCM. Okay, where I is the inertia about the pivot point, not about the center of mass. So oftentimes these problems are connected to the parallel axis theorem, because you might know the inertia about the you might know the inertia about the center of mass, but you don't know the inertia about the pivot point. And so you use the parallel axis theorem to determine the inertia about the pivot point. Okay. And a final type of system we discussed was if you have a u of x graph, okay, we showed that if a particle has is near an equilibrium, it will undergo simple harmonic motion about the equilibrium. Okay, and the reason is that near an equilibrium, the potential can be approximated as a parabola. Okay, and so in that case, so this is the period of small oscillation. If the oscillation is too big, then it can go into another equilibrium point. So the period of small oscillation is equal to 2 pi square root of m over u prime prime evaluated at the equilibrium position. So because this one has two different equilibrium points, it's going to have two different what am I trying to say? Periods of oscillation. One for oscillation here, one for oscillation here. We talked about energy in the mass spring system. Okay. And in the mass spring system, we have kinetic energy and potential energy. The kinetic energy is 1/2 mv squared. The potential energy is 1/2 kx squared. All right. And so that can be thought of in two different ways. You could have, you could evaluate this energy at the moment it passes through equilibrium, in which case all of the energy is kinetic. So you have 1/2 mv max squared. Or you could analyze it in terms of at the extreme point where there's no kinetic energy, in which case the total amount of energy is 1/2 ka squared. It's all potential. So then we just use this to solve some energy problems. All right. So that is my review of second semester content. So I'm going to see you in the Zoom room to catch up quickly and just touch base, and then I'll probably let